Ancient builders measured the Earth with near-perfect accuracy long before modern science existed. By the end of this video, you will understand the forgotten techniques that made this possible, methods so advanced they still puzzle researchers today. How did they map continents using only shadows and stars? What secrets are hidden in the alignment of their greatest monuments? Their story forces us to reconsider the limits of human ingenuity. What does it truly mean to understand the world around us? We often think of measuring the planet as a modern scientific triumph. Yet the very science that makes it possible, geodesy, has roots stretching back to the earliest civilizations. This is the art and science of measuring the Earth itself, a discipline born not in a laboratory but from the most fundamental human needs. Ancient societies depended on predicting the annual flood of the Nile for their survival, a cycle dictated by the stars. They needed to navigate vast, featureless oceans and build structures that would stand for generations. These were not abstract puzzles but urgent, practical challenges. Their solutions emerged from a deep, sustained observation of the world around them. They watched the sun and stars, noting how their paths shifted with the seasons. They developed simple but effective tools to track angles and measure distances across the land. This was not random guesswork. It was a deliberate, systematic process of turning observation into reliable knowledge. The principles they established, the first steps in a long scientific journey, created the essential foundation. Without this groundwork of celestial observation and practical mathematics, the later, more stunning measurements of the Earth's size would have been impossible. They were learning to read the language of the planet itself, a language written in shadows, stars, and the lines on the ground. The night sky was their unchanging map. Long before the invention of the magnetic compass, ancient navigators looked upward to find their way across the world. They noticed something profound. While most stars appear to wander throughout the year, a few hold their positions with remarkable consistency. The North Star, Polaris, became a fixed point of reference, a celestial beacon that never strayed from its post directly above the Earth's North Pole. A sailor simply needed to measure the angle between the horizon and this steady star to know their latitude, their precise north-south position on the globe. This single observation transformed the open ocean from a trackless void into a grid that could be read and followed. This celestial knowledge was not limited to the seas. On land, builders encoded the same principles into stone. The Great Pyramid of Giza, for instance, is aligned to the cardinal directions with an accuracy of 1/15th of a single degree. How was such precision achieved without modern tools? The answer likely lies in tracking the circumpolar stars, those that never rise or set but instead circle the pole. By marking the points on the horizon where a specific star both rose and set, an observer could bisect that arc to find true north. This was not a one-time event but a process of patient, repeated observation, turning the slow wheeling of the heavens into a permanent terrestrial reference. Other cultures built monuments that acted as massive solar and lunar calendars. Stonehenge, with its iconic heel stone, captures the exact moment of the summer solstice sunrise. The Intihuatana stone in Machu Picchu functions as a sophisticated astronomical clock. These structures are far more than ritual sites. They are precise instruments of measurement, engineered to lock in the relationship between the Earth and the Sun. By marking the solstices, the days when the Sun reaches its highest and lowest points in the sky, these builders could determine the length of the year and understand the cyclical nature of the seasons. This was critical knowledge for agriculture, for ceremony, and for creating a stable, predictable calendar. The most daring application of this celestial science was on the open ocean. Polynesian voyagers undertook journeys of thousands of miles across the Pacific, navigating by the stars long before European explorers dared to leave the sight of land. They memorized the paths of specific stars, knowing that each one rose and set at a fixed point on the horizon. A star that passed directly over their home island would become their guide. As they sailed, they would follow that star's path, understanding that its position would change as they moved east or west. They were effectively sailing across a star chart, using the sky not just for direction, but to maintain their longitudinal course. This intimate knowledge of the celestial sphere hints at an early, practical understanding of the Earth as a sphere, a world that could be mapped and traversed by the fixed points of light in the night sky. A single stick planted upright in the Earth can reveal the fundamental geometry of our world. This simple tool, known as a Gnomon, was the key that unlocked one of history's most stunning calculations. Across ancient cultures, from Egypt to China, observers noted that the length of a shadow cast by a Gnomon changed not only with the time of day but also with the seasons. The sun's highest point at noon on the summer solstice produced the shortest shadow, while its low arc on the winter solstice created the longest. This was more than a way to mark time. It was a direct measurement of the sun's angle in the sky. By carefully tracking these angles, these early scientists inferred that the Earth itself must be curved. If the world were flat, the sun's rays would strike every location at the same angle at the same moment, and shadows would be identical everywhere. But they were not. This crucial discrepancy became the foundation for a legendary experiment. The Greek scholar Eratosthenes, head of the Great Library of Alexandria, took this principle and applied it on a grand scale. He learned of a fascinating observation from the city of Syene, located far to the south. There, at noon on the summer solstice, the sun shone directly overhead, casting no shadow at the bottom of a deep well. The columns in Alexandria, however, still cast a distinct shadow at that very same moment. Eratosthenes realized these two cities sat on different points of a curved surface. He measured the angle of the shadow in Alexandria, finding it to be about 7 degrees or 1/50th of a full circle. All he needed then was the physical distance between the two cities. Once he had that measurement, the rest was a matter of elegant geometry. If 7 degrees of the Earth's circumference equaled the distance from Alexandria to Syene, then the entire 360-degree circle must be 50 times that distance. His final calculation for the Earth's circumference was astonishingly close to the modern value, achieved with little more than a stick, a deep well, and the power of human reason. This was not an isolated feat of genius but a testament to a universal method. The same principles of shadow and angle were used to align the world's most enduring monuments. The vast foundations of the Great Pyramid were laid out with breathtaking precision, using nothing more than a central gnomon and careful tracking of its shadow's path throughout the day. By marking the points where the tip of the shadow touched a circle drawn around the stick at different times, they could establish a perfect east-west line. This simple yet profound technique, accessible to anyone with a sunny day and a sharp eye, allowed for the creation of structures that would stand for millennia. It demonstrates a profound truth about our ancestors. They possessed the ability to extract cosmic knowledge from the most ordinary of events. The shifting of a shadow was not just a daily occurrence, it was a data point in a vast, silent conversation with the universe. Water itself became a ruler for the ancient world. Its unwavering surface, always seeking a perfect horizontal plane, provided a constant reference in an uneven landscape. From the sprawling Mesopotamian plains to the 7 hills of Rome, engineers harnessed this simple principle to achieve the impossible, moving water across vast distances with breathtaking precision. They constructed canals and aqueducts that snaked through hills and valleys, maintaining a gradual, consistent slope for miles. How could they ensure a channel cut through solid rock would drop just the right amount over its entire length? Their methods were brilliantly straightforward. They used long, water-filled trenches as massive liquid levels, or they employed a simple sighting tool called a chorobates. This was a long, leveled table with plumb lines hanging from its ends, allowing surveyors to visually line up a straight, gradual descent across the terrain. This was not guesswork, it was careful, methodical engineering. The result was a network of waterways that transformed arid lands into fertile breadbaskets, sustaining entire cities. This hydraulic mastery did more than irrigate crops. It gave these builders an intimate, practical understanding of the land's contours. To move water from a mountain spring to a distant city, they had to map the subtle folds of the earth, calculating elevations and distances with remarkable accuracy. Their canals became the Panama Canals of the ancient world, monumental projects that reshaped geography itself. In manipulating water to serve human need, they were quietly compiling a vast, unwritten survey of the planet's topography. Every canal was a lesson in the shape of the world, a line drawn in water and stone that proved our ancestors could not only measure the Earth from the stars, but could also chart its every slope and valley with nothing more than the calm, level surface of a still pool of water. A simple rope stretched taut between two stakes became one of the most powerful tools in the ancient builder's arsenal. This humble cord, often knotted at precise intervals, was the physical link between abstract geometric principles and the monumental structures that rose from the earth. The Egyptians elevated this practice to a sacred art, a ceremony known as stretching the cord. In this ritual, priests would align the rope with the positions of specific stars, most notably the circumpolar stars that never set. By anchoring their terrestrial measurements to the fixed points of the celestial sphere, they were ensuring that their temples and pyramids were not merely buildings but reflections of cosmic order. The rope was more than a tool, it was a conductor for bringing heavenly precision down to the human scale. This process relied on the creation of a standardized unit of measurement, and the most famous of these was the royal cubit. This was not an arbitrary length. It was derived from the human body, specifically the distance from a man's elbow to the tip of his middle finger, and it was meticulously reproduced on stone rods to ensure consistency across every project. This meant that every architect, every foreman, and every worker was building from the same blueprint, a shared language of length that allowed for the coordination of thousands of laborers over decades. From the vast base of the Great Pyramid to the intricate chambers within, every dimension was a multiple of this fundamental unit, creating a harmony of proportion that still resonates today. The true power of the rope was unlocked when it was combined with simple geometric rules. Builders knew that a triangle with sides measuring 3, 4, and 5 units would always contain a perfect right angle. This is the famous 3-4-5 triangle, a cornerstone of practical geometry. A team could lay out a perfect square or rectangle for a building's foundation by taking a long rope, knotting it into 12 equal segments, and having workers pull it taut to form a triangle with sides of 3, 4, and 5 segments. The angle between the 3 and 4 unit sides was guaranteed to be exactly 90 degrees. This was not abstract mathematics taught in a school. It was applied knowledge performed with physical effort in the dust and sun. Imagine the scene on the Giza Plateau. Under the blazing sun, teams of workers are pulling these knotted cords taut across the limestone bedrock. Their shouts and the strain of the rope are the only sounds as they carefully adjust the stakes, checking and rechecking the alignment until the geometry was perfect. They were creating the foundational lines for a structure that would stand for millennia, using a method so simple and so brilliant that its accuracy is undeniable. These ropes were their lasers and theodolites, transforming a chaotic landscape into a grid of perfect angles and straight lines. This hands-on, systematic approach demonstrates a profound truth that the highest achievements of human ingenuity often spring from the mastery of the most basic tools. The precision of the pyramids was not a mystery bestowed by outsiders, but the direct result of patient, intelligent, and utterly human work. The land itself was their ultimate map. Ancient builders did not just look to the stars or stretch cords across the sand. They read the permanent script written in the contours of the earth. Mountains were not obstacles but fixed reference points, timeless sentinels that anchored their understanding of space. Rivers and coastlines became the flowing lines of this natural chart, defining territories and pathways through an otherwise trackless wilderness. This was geomorphic landmark mapping, a technique of profound intimacy with the environment. It required a navigator to hold a mental image of the land, to triangulate their position by sighting the angles between a distant peak, a distinctive rock formation, and the bend of a river. Indigenous cultures across the Americas perfected this art. A traveler in the vastness of the Andes could find their way by memorizing the unique silhouette of a specific volcano against the sky. A canoeist navigating the complex waterways of the Pacific Northwest knew that a certain confluence of rivers marked the boundary of their people's lands. They were creating cognitive maps of immense scale and accuracy, passed down through generations in stories and songs, not on parchment. This method reveals a symbiotic relationship with the world, where every hill and valley had a name and a meaning. The landscape was not a resource to be conquered but a partner in the journey, a living atlas that guided exploration and shaped the very pattern of settlement. To walk that land was to read a story, one where the path forward was always written in the lay of the land itself. But the greatest of these methods transformed entire landscapes into permanent observatories. Structures like Stonehenge on the English Plain or the unique Caracol Tower at Chichen Itza were far more than ceremonial grounds. They were precision instruments carved from stone, designed to track the slow dance of the heavens. Their alignments are not approximate. The central axis of the caracol is carefully oriented toward the setting sun on the spring equinox, while its narrow windows frame the extreme positions of Venus. At Stonehenge, the heel stone captures the first ray of the summer solstice sunrise, a moment that marked the turning of the year for the people who built it. These were not passive monuments, they were active tools for prediction. By watching where a planet rose or set against a specific stone, ancient astronomers could forecast the changing seasons, anticipate celestial events, and maintain an accurate calendar essential for planting and harvest. This was a science written in alignment, a permanent record of celestial mechanics. The consistency of these alignments across different cultures points to a shared discovery. The slight wobble in the Earth's tilt, a cycle stretching over thousands of years, subtly changes our view of the stars. The fact that these structures so accurately account for the sky as it was in their own time provides modern researchers with a fixed point, a data set locked in stone. It reveals that these builders understood the regularity of celestial cycles, and they used that knowledge to measure not just time, but the very orientation of our planet in space. We can think of these places as the ancient world's supercomputers. Their processing power was the movement of the sun and moon. Their memory was the immutable position of their stones. They encoded generations of observational knowledge into a form that could outlast any parchment or spoken word, a legacy in rock for future generations to decipher. This global effort to align human creation with cosmic order speaks to a profound desire to find our place in the universe. to build a connection between the earth we walk on and the infinite sky above. The silent language of mathematics was etched into the very stones of the ancient world. Beyond the knotted ropes and celestial alignments, builders employed a hidden system of ratios and proportions that gave their structures a profound, almost musical harmony. They discovered that certain numbers and relationships held a special power, creating forms that were not only stable but also deeply pleasing to the human eye. This was the art of sacred geometry, where abstract constants became the invisible framework for their greatest achievements. The Great Pyramid of Giza stands as the ultimate testament to this principle. Its base perimeter, when compared to its original height, produces a ratio that is remarkably close to 2 times pi. This is not a coincidence. It suggests its designers intentionally encoded a fundamental mathematical constant, a value representing the relationship between a circle's circumference and its diameter, into the pyramid's very form. This was more than an architectural flourish. It was a way of scaling cosmic knowledge into a terrestrial monument. By using such ratios, a master builder could dictate the proportions of an entire structure from a single, standardized measurement. If you knew the length of one side, the height, the slope, and the inner chambers were all determined by an unchangeable mathematical rule, this system guaranteed consistency across a project that might span decades and involve thousands of workers, all without a single blueprint as we know it. A simple fraction could indeed determine the height of a temple, and a repetitive ratio could dictate the layout of an entire city. The same proportional logic appears in classical Greek temples, where the precise relationship between a column's width, height, and the spacing between columns was governed by strict mathematical orders. This is why these structures feel so balanced and timeless. Their beauty is rooted in an invisible numerical order. This approach transformed mathematics from a silent partner into the co-architect of the ancient world. It was the tool that allowed them to translate a vision of cosmic order into the enduring reality of stone, creating a legacy where art and science were beautifully and inseparably one. The journeys of ancient explorers became a living, breathing atlas of the world. While monuments stood still, people moved, and in their movement, they gathered the most vital information about the planet's scale. Along the sprawling network of the Silk Road, merchants did more than trade silk and spices. They meticulously recorded the rhythm of their travels, the number of days between oases, the direction of mountain passes, the position of the stars over unfamiliar deserts. All of this was data. A single caravan leader might know only his own route, but when these logs were shared and compared across generations, they wove together into a vast, collective understanding of continental distances. This was not a single map drawn by one hand, but a mosaic of countless experiences, stitched together through story and memory. Phoenician sailors, venturing beyond the Mediterranean into the Atlantic, kept similar records. They noted how the constellations shifted over weeks at sea, how the sun's path changed, and how long it took to sail from one landmark to the next. These voyages were not just feats of courage, they were acts of measurement. A captain's log was a precious document, a string of data points that transformed a treacherous, unknown ocean into a navigable space. Think of each journey as a single line drawn across a global canvas. One trader's path from Rome to China, another's voyage from Egypt to Britain, a third's coastal trek around India. Over centuries, these countless lines began to overlap and connect, revealing the true shape and staggering size of the continents they crossed. How wide was Asia? The answer was not found in a single calculation, but in the accumulated days of countless camel caravans. How vast was the open sea? The answer was in the provisions stored on a ship and the number of sunrises witnessed before sighting land. This method relied on the most fundamental human experiences, time and direction. By converting travel time into distance, these ancient societies could estimate the breadth of a desert or the width of an ocean with surprising accuracy. Their maps were not drawn with the precision of a satellite, but they captured the relational truth of the world, a knowledge born from the dust of the road and the salt of the sea. This was how human adventure, one step at a time, slowly and surely mapped the entire Earth. The stories told around ancient campfires were far more than simple entertainment. They were living maps encoded with the precise geography of a people's world. Across countless cultures, spiritual myths and creation narratives preserved complex measurements and spatial relationships through the power of symbolism. In Australia, the intricate songlines of Aboriginal Dreamtime stories trace the paths of ancestral beings across the continent. Each verse in a song corresponds to a specific landmark, a waterhole, a mountain range, or a particular tree. By singing the song in the correct order, a traveler could navigate vast, featureless deserts, the melody itself becoming a sonic map of the journey. This was a profound fusion of culture and science, where the rhythm of a song held the data for survival. Similarly, Norse sagas are filled with celestial references, not just as poetic imagery but as practical navigational aids. The myth of the god Odin hanging from the world tree, Yggdrasil, can be interpreted as an allegory for polar alignment, a story embedding the concept of a central, unchanging axis in the cosmos around which everything else revolves. These narratives were durable, passed down through generations, ensuring that critical knowledge about the stars and the land outlived any single individual. A legend about a great serpent creating a winding river might secretly describe its actual course and length. A tale of a hero chasing the sun could encode the solar path at a specific latitude. This symbolic geometry allowed entire communities to carry a sophisticated understanding of their environment within their collective memory. Storytelling became the most resilient form of cartography, one that could not be washed away by floods or fade on parchment. It was a way of weaving the physical world into the cultural fabric, ensuring that the knowledge of how to measure and navigate the Earth was preserved not in a library, but in the very soul of the people. A landscape itself could be calibrated like a vast, silent instrument. Across the plains of Peru, the Nasca lines stretch for miles, their immense geometric forms and animal figures visible fully only from the air. While their purpose remains a subject of fascination, one compelling theory suggests they functioned as a permanent geodetic network. These were not random drawings but precisely placed markers, aligned with distant mountain peaks, the flow of underground water, and key points on the horizon where the sun and moon would rise and set. Each line, each trapezoid, acted as a fixed reference point in a grand survey of the region. By walking these lines, ancient surveyors could constantly check and recalibrate their measurements for water channel projects or agricultural terraces, ensuring that every new construction fit perfectly into the existing spatial order. This was not a short-term endeavor. Maintaining the clarity of these lines against wind and erosion required a sustained, communal effort across generations. It represents a breathtaking level of long-term planning and social coordination, a shared commitment to preserving a precise understanding of their world. These markings transformed the entire valley into a living map, a testament to the human impulse to not just live within a landscape, but to actively measure it, mark it, and weave it into a coherent, human-made design. The natural world itself was an open book, its pages written in the flight of birds and the movement of herds. Ancient peoples did not merely live within their environment, they were fluent readers of its subtle language. They understood that the seasonal journeys of animals were not random. but reliable indicators of distant geographies and shifting weather. A hunter watching caribou herds move to their wintering grounds was not just tracking prey, he was learning the layout of the land beyond the horizon. The path of the animals became a living trail, revealing mountain passes, river fords, and sheltered valleys that might otherwise remain unknown for generations. Farmers, too, were astute observers. The arrival of specific bird species signaled the perfect time to plant certain crops, their migration a more accurate calendar than any human-made device of the era. This biogeographic method transformed instinct into intelligence. Following a dense flock of geese flying north in the spring was not just an observation, it was a navigational command. It implied the existence of breeding grounds, of summer waters, and abundant food sources in a land far away. Early Polynesian explorers are believed to have used this very principle, watching the directional flight of birds at dusk to guide their canoes toward unseen islands. The animals were their scouts, their natural compasses pointing the way across the trackless ocean. This intricate knowledge created a profound connection between human survival and ecological wisdom. The rhythms of nature were not separate from daily life. They were the essential framework for it. To know when the salmon would run upstream was to know when your community would eat. To understand the grazing patterns of bison was to know where to find them on the vast plains. This was a form of measurement that went beyond distance. It measured time, abundance, and opportunity. It was a silent partnership with the planet where every creature, from the smallest songbird to the largest whale, played a part in a grand, interconnected system of guidance. Our ancestors learned to listen, and in doing so, they discovered that the Earth was not a silent rock, but a world brimming with information, waiting only for a watchful eye to understand its rhythms. Even silence could be measured. In the vastness of a mountain canyon or the echoing darkness of a subterranean cavern, ancient innovators discovered that sound itself could become a ruler. By listening intently to the return of a shout or the sharp crack of two stones struck together, they could estimate the dimensions of a space they could not fully see. This was acoustic measurement, a method that transformed an invisible wave into a practical tool for understanding distance. Deep within mine shafts, workers might tap on a wall and judge the depth of a tunnel by the quality of the echo, a hollow ring suggesting a large chamber behind the rock, while a dull thud indicated solid earth. This was not guesswork, but a refined sensory skill born from experience, a way of hearing the shape of the world. In sacred architecture, this principle was elevated to an art form. Certain temples and tombs were designed with astonishing acoustic properties, where a single spoken word or a specific chant would resonate through the hall, creating a sustained echo or even amplifying a particular harmonic frequency. Researchers suggest these spaces were engineered to enhance ritual experiences, where the very sound of a prayer became a physical force, filling the chamber and seemingly connecting the human voice with the structure itself. This auditory dimension reveals a profound layer of ancient thought, where measurement was not solely a visual or mathematical exercise. It was a holistic practice that engaged all the senses, proving that even in the absence of light, human curiosity found a way to map the unknown. The echo in the canyon was not just a sound, it was a conversation with space, a momentary bridge across a distance measured not in steps, but in the time it took for a voice to travel and return. Commerce created the first global network of information. In the bustling marketplaces of the ancient world, caravans from the Indus Valley met traders from Mesopotamia, their transactions involving more than just spices and textiles. They exchanged stories of mountain passes, the flow of great rivers, and the number of days it took to cross a desert. Every merchant's logbook, filled with notes on travel times and local landmarks, became a page in a vast, unwritten atlas. This was not merely business, it was a sophisticated data-gathering operation. The very existence of a trade route for lapis lazuli, a stone found only in a single region of Afghanistan, implied a known and measured path stretching thousands of miles to the palaces of Egypt and the temples of Sumer. By analyzing which goods came from where and how long they took to arrive, ancient economists could begin to infer the staggering scale of continents. They understood that a long journey by sea meant a vast ocean, and a slow caravan moving overland hinted at the breadth of an entire subcontinent. The trade patterns themselves painted a map. A dense network of routes in a region like the Mediterranean revealed it was a connected inland sea. In contrast, the sparse but long-distance exchanges across the Sahara Desert suggested an immense, challenging emptiness separating distinct cultural worlds. This commercial intelligence was a form of collective learning. A single merchant might only know his own route, but when his knowledge was pooled with that of countless others in a major trading hub, a clearer picture emerged. The bustling port of Oman became a living database where sailors from India shared charts with captains from East Africa, slowly piecing together the outline of the Indian Ocean. In this way, the relentless human drive for material wealth quietly funded the greatest exploration project in history. Every bale of silk, every sack of pepper, carried with it a hidden cargo of geographic truth, proving that the desire for connection and the pursuit of knowledge have always traveled the same road. The moon's gentle light offered a different kind of clock. While the sun marked the day, our planet's constant companion carved the months with its rhythmic cycle of phases. Ancient astronomers saw in this lunar dance a reliable measure of time, one that also governed the powerful push and pull of the ocean tides. From the shores of the Mediterranean to the islands of the Pacific, observers linked the moon's position to the sea's behavior, understanding that this gravitational connection was a force that could be predicted and mapped. This was more than just tracking time. It was about recognizing a cosmic relationship that directly shaped the human world, influencing everything from navigation to harvests. The Babylonians elevated this observation into a precise science. For centuries, their scholars meticulously recorded every lunar eclipse, noting the exact timing and duration of each event. This long-term data collection revealed a repeating pattern, a celestial rhythm that allowed them to predict future eclipses with remarkable accuracy. Their lunar calendars were so finely tuned that they could be adjusted over long periods, creating a stable and predictable system for their society. This lunar-focused approach provided a crucial counterpoint to solar measurements, creating a dual celestial framework that cross-checked and refined their understanding of the heavens. But an eclipse held an even deeper secret. During a total lunar eclipse, when the Earth moves directly between the Sun and the Moon, our planet casts its shadow upon the lunar surface. To an ancient observer, this was not just a darkening, it was a revelation. The edge of that shadow, as it crept across the face of the Moon, was always gently curved. This consistent curve, visible during every single eclipse, served as a powerful, recurring piece of evidence that the Earth itself was a sphere. That moment of darkness, witnessed by countless generations, quietly illuminated one of history's greatest puzzles, offering a direct glimpse into the shape and scale of our world. The very stone used to build a monument carried a hidden map within it. A block of granite, a slab of limestone, or a pillar of bluestone was more than just a building material. It was a physical piece of a distant landscape, and its journey to the building site represented a profound understanding of geological boundaries and regional composition. Ancient builders were not merely construction workers, they were the first geologists, reading the story of the Earth written in the layers of rock and the unique signatures of minerals. When they traveled to a specific quarry, often located dozens or even hundreds of miles away, they were not just collecting stone, they were collecting data. They learned to identify the outcrops that offered the hardest granite for foundations, or the finest sandstone for detailed carvings. This knowledge of where to find specific resources and how to transport them across challenging terrain required a sophisticated mental map of the land's underlying structure. The journey of the Bluestones to Stonehenge stands as a powerful testament to this method. These distinctive stones were not local to the Salisbury Plain. They were quarried from the Preseli Hills in distant Wales, a monumental journey of over 150 miles. Transporting these massive stones, whether by land on wooden rollers or by a combination of river and coastal routes, required an intimate knowledge of the entire geography between the 2 points. The builders needed to know the paths through forests, the firmness of riverbanks, and the safest passages across hills. This was not a random expedition. It was a carefully planned logistical operation that proved they understood the distances and physical challenges of their island on a continental scale. Every stone that arrived at the site was a triumph of navigation and terrain knowledge, a piece of Wales deliberately integrated into the heart of England. This geological awareness extended far beyond mere procurement. The choice of specific stones often carried deep cultural and symbolic meaning, linking the power of a place to the structure being built. A sculptor selecting marble from a particular mountain vein was not just choosing a beautiful material, he was consciously drawing upon the essence of that location, believing its unique properties would be transferred into the finished work. In this way, the pyramids of Egypt, built with limestone from the Giza Plateau itself and granite floated down the Nile from Aswan, become more than tombs. They are a geological collage of the kingdom. The act of building was an act of unifying the land, of physically connecting distant regions into a single, coherent expression of power and understanding. The stones themselves were the ultimate teachers, their weight and texture and origin silently instructing generations of builders about the composition of their world, turning every quarry into a classroom and every monument into a lesson in the Earth's deep history. A ship's crew could feel the planet turning beneath them. They could not see the Earth's rotation, but they could read its effects in the language of the sea and sky. For the master navigators of Polynesia, the ocean was never a blank expanse. It was a dynamic, textured landscape of moving forces. They learned to interpret the dominant trade winds, steady currents of air that blew with predictable consistency. A wind from the northeast meant one thing, a shift to the southeast meant another. These were not random breezes, but the planet's great atmospheric rivers, and by sensing their direction and strength on his skin, a navigator could hold a course for weeks without ever seeing land. This was a living science passed from elder to apprentice, not in a classroom, but on the deck of a voyaging canoe. The student would learn to distinguish dozens of distinct wave patterns, each one a signature of distant weather or unseen shores. A long, rolling swell might originate from a storm thousands of miles away, while a confused, choppy sea could suggest the reflection of waves from a nearby island, still hidden beyond the horizon. Even the clouds told a story, a stationary, puffy cloud formation in an otherwise empty sky, often gathered over the warm landmass of an atoll, its very presence betraying the location of an island the naked eye could not yet find. This knowledge transformed the Pacific from a barrier into a pathway. A navigator would lie in the bottom of his canoe, feeling the vessel's pitch and roll, reading the ocean's rhythm through his very bones. He was not just sailing on the water, he was navigating through a three-dimensional space of wind layers and current depths. This profound, intuitive understanding of fluid dynamics allowed them to measure the sea itself. They knew that a certain sequence of swells, combined with a specific wind and a particular type of cloud, meant they were precisely 10 days' sail from a specific island group. The distance was measured not in abstract units, but in the lived experience of the journey, in the number of sunrises it took for the ocean's story to reach its next chapter. Their canoes became instruments of measurement, their sails catching the planet's breath to explore a world they had mapped not on parchment, but in the very currents of air and water. Geometry was the sacred language of the cosmos, spoken in stone. When ancient builders laid out a temple or a city, they were not simply constructing a building, they were inscribing a model of the universe itself. The circle represented the celestial sphere, the eternal cycle of the seasons. The square stood for the four cardinal directions, the stable, measurable Earth. Together, these forms created a mandala, a cosmic diagram that mapped the relationship between heaven and the human world. This was not mere decoration. It was a profound statement that the same mathematical principles governing the orbits of planets also governed the ideal proportions of a sacred space. A visitor walking through such a temple was not just moving through rooms, they were journeying through a symbolic representation of cosmic order, learning the fundamental geometry of existence with every step. This philosophy appears with stunning consistency across the globe. In the intricate mandalas of Hindu and Buddhist temples, concentric circles and squares map out spiritual realms, but they also encode astronomical knowledge. The positions of gates often align with solstice sunrises or the path of specific stars. Similarly, the great ceremonial plazas of Mesoamerican cities like Teotihuacan are precisely aligned to cardinal directions, their lengths and widths reflecting ratios that mirror the relationship between the Earth's orbital period and the lunar cycle. The entire city becomes a calendar, its streets and structures a physical expression of time. This symbolic approach served a vital educational purpose. In an era before widespread literacy, architecture was the textbook. The very design of a building taught complex concepts of geography, astronomy, and mathematics. A priest could point to the central axis of a temple, explaining how it represented the world tree or the axis mundi, the central pole around which the stars revolved. This was a direct, tangible way to convey the idea of a spherical Earth with poles and an equator. The spirals carved into Neolithic tombs in Ireland, which mirror the swirling patterns of galaxies, taught a lesson on scale, suggesting that the same creative force was at work in the vast cosmos and in the small, dark chamber of a tomb. This was where science and spirituality became one. The drive to understand the world was inseparable from the wonder of its divine creation. To measure the Earth was to understand the mind of the Creator, and to build in harmony with those measurements was an act of worship. The perfect proportions of the Parthenon in Greece, based on the golden ratio, were not just an aesthetic choice, they were believed to be a glimpse into a divine, underlying harmony that connected art, nature, and the human soul. In this unified worldview, a simple geometric pattern etched into a floor was far more than art. It was a philosophical argument, a scientific thesis, and a spiritual map, all speaking the silent, universal language of shape and number. The soil itself became a living calendar. For the vast majority of ancient people, survival was measured not in years but in harvests. The success of a community depended on knowing precisely when the rains would arrive, when the river would flood, and when the days were long enough to plant the seeds. This was not a leisurely academic pursuit, it was a matter of life and death, and it forced farmers to become the world's most practical astronomers. They watched the horizon like a clock, noting where the sun rose each morning. A shift in its position along a distant mountain range marked the slow march of the seasons, telling them when to prepare the fields. The Maya, for instance, did not just create a calendar, they engineered an interlocking system of them. They tracked a 260-day sacred year alongside a 365-day solar year, synchronizing them over a vast cycle to create a precision instrument for agriculture and ceremony. This allowed them to predict the coming of the rainy season with remarkable accuracy, dictating when to clear land, when to plant maize, and when to harvest. Their calendar was their agricultural blueprint, a complex piece of social software that organized an entire civilization. This deep timekeeping transformed how they measured and divided the land itself. A farmer would lay out his fields in accordance with these celestial cycles, using standardized units of length to create plots that could be efficiently managed and their yields accurately predicted. The size of a field was not arbitrary. It was a calculation based on how much food a family needed and how many days of sun and rain the calendar promised. This practice generated a wealth of geographic data, as generations of farmers documented which plots flourished under which conditions, creating a living map of soil quality and microclimates. Think of a community elder looking up at the Pleiades star cluster just before dawn. Its first appearance in the morning sky was a signal, a celestial alarm clock that told everyone it was time to begin the new planting season. In that moment, the vast, impersonal cosmos was translated into a direct, actionable command. The sky was not an object of distant wonder, it was the most important tool in the shed. This intimate dance with the planet's rhythms, born from the simple need to eat, represents one of humanity's most profound and enduring partnerships with nature. It demonstrates how the most fundamental human necessities, the daily acts of survival, became the very engine that drove our understanding of the world's grand design. A river's current is a story told in water, a continuous narrative of the land it has crossed. Ancient civilizations did not merely live beside these waterways, they learned to read them, understanding that every twist in the course and every type of sediment carried by the flow was a clue to a much larger geographic puzzle. This was hydrological mapping, a science that transformed rivers into dynamic, living maps. In China, master hydrologists of the Yellow River Basin faced a constant challenge: the river's devastating floods. To tame it, they had to understand it. Teams of surveyors traveled its length, meticulously charting its main channel and countless tributaries. They measured the speed of the current at different points and analyzed the composition of the silt it deposited. Heavier, coarser sand indicated a nearby mountainous source, while fine, fertile clay suggested a long journey across peaceful plains. From this data, they could infer the entire character of the upstream landscape, the steepness of distant slopes, the rock types of faraway highlands, and the overall shape of the continent's drainage basin. This knowledge was power. It allowed them to engineer vast canal systems that redirected floodwaters and irrigated endless fields, projects that literally defined the borders and breadbaskets of empires. The river itself became the empire's main artery and its most accurate map. Similarly, for the Egyptians, the Nile was more than a source of life. It was a relentless teacher. Its annual flood was a predictable event, but the height of the floodwaters was not. A flood that was too low meant famine, while one that was too high meant destruction. Priests and officials therefore established nilometers, elaborate staircases, and wells to measure the river's rise with precision. But they realized something profound. The timing and nature of the flood, the color of the water, and the specific mix of sediments it carried were all messages from the interior of a continent they had never seen. They understood that this life-giving water had traveled from impossibly distant sources, from a land of great lakes and torrential seasonal rains far to the south. The river was their only connection to this mysterious heart of Africa, and by reading its flow, they were effectively measuring the vastness of the continent itself. Every drop of water was a messenger, and every bend in the river was a chapter in a geographic epic that stretched for thousands of miles. A royal court listens, captivated, as a traveler describes mountains of jade and cities where silk flows like water. These were the moments when the world grew smaller. Long before satellites, the most reliable maps were drawn not on parchment, but in the memories of diplomats and explorers who walked the earth. Official envoys sent on missions of state became unwitting agents of science. Their primary duty was to secure alliances or negotiate trade, but their most enduring legacy was the knowledge they carried home. A Chinese ambassador returning from a journey along the Silk Road would report not only on the strength of a distant king's army, but on the width of the deserts he crossed and the height of the mountain passes. His detailed logs, intended for the emperor's eyes, became priceless entries in a growing geographic database, stitching separate kingdoms into a single, understood continent. This was a collaborative project spanning civilizations. When a Babylonian scholar shared a star chart with an Egyptian priest, or when a map from the Library of Alexandria was copied for a library in Persia, they were doing more than exchanging information. They were cross-referencing observations, verifying distances, and standardizing measurements. A unit of length used in one kingdom could be compared to the cubit of another, allowing for the first true approximations of continental scale. The travels of figures like Marco Polo are the most famous examples, but for every well-known name, there were hundreds of unnamed merchants and diplomats whose collective experiences slowly filled in the blank spaces on the mental map of the ancient world. Think of the scene in a bustling port city. A Greek geographer questions a ship's captain from India about the monsoons. A Roman engineer studies the plans for a Persian Qanat, a subterranean water channel, and brings the concept home. In these exchanges, curiosity and politics became the engine of discovery. A king's desire for a new trade route could fund an expedition that would reveal the true shape of a coastline. A peace treaty between two empires would open borders, allowing for the free flow of not just goods, but of ideas about how to measure and navigate the land. This diplomatic network created a feedback loop of incredible power. Each new account verified or corrected an old one. A story about a great southern land, once considered a myth, would be corroborated by a second and a third independent report, until it was accepted as geographic fact. The world picture that emerged was a patchwork, a quilt of countless individual journeys, slowly sewn together into a coherent whole. It was through this slow, deliberate, and collective effort that the continents began to take their familiar shape in the human mind, long before any single person could ever see them from above. A Roman legionary stationed in the damp chill of northern Britain would have found his new home strangely familiar. The fort he entered, with its precise rectangular layout, its central via Pretoria, and its standardized granaries, was an exact copy of the one he had left behind in the sun-baked hills of Syria. This was not a coincidence, it was a continent-spanning experiment in measurement. By replicating the same architectural blueprint across thousands of miles, Roman military engineers were conducting a form of quality control on a planetary scale. They used the same units, the same foot, the same pace to lay out foundations from the Rhine to the Nile. When they built a perfectly square fort in Egypt, they expected it to be perfectly square. But as they applied their rigid, standardized plans to the curved surface of the Earth, subtle discrepancies would inevitably appear. A long, straight road, built with impeccable precision using local measurements, might slowly drift from its intended alignment over a great distance. These tiny, accumulated errors were not failures, they were priceless data. They were the Earth itself whispering its true curvature to those who knew how to listen. This replication created a network of fixed points, a global grid of human-made geometry that could be used to test and refine their understanding of the world's shape. The consistent application of a single measurement system, from a humid British riverbank to a windswept Jordanian desert, proved that universal principles could be applied anywhere. It demonstrated that the human mind could conceive of a perfect form, a standard module, and then impose it upon the varied face of the planet. This process turned every construction project into a calibration point. An engineer in Gaul could compare his results with a report from a colleague in North Africa, and together they could ask a profound question. Did their shared standard of length change over vast distances? Did the Earth's geometry demand adjustments that their flat plans could not anticipate? The relentless repetition of the same design, from temples to aqueducts, was a powerful tool for discovery. It was through this monumental act of copying, of building the same thing again and again across a continent, that they could finally see what was different. And in those differences, hidden in the silent stones of 1,000 identical forts, lay the secrets of the Earth's grand spherical design. Even the stars were read as a language of destiny. Across the ancient world, the practice of astrology demanded a meticulous, almost obsessive observation of the night sky. While its purpose was to divine the future or understand the will of the gods, the methods were anything but vague. Babylonian priests, for instance, maintained detailed clay tablet diaries, logging the precise movements of planets against the backdrop of fixed stars. They noted when Venus appeared as the morning star, tracked the retrograde path of Mars, and recorded the timing of lunar eclipses. This was not random stargazing, it was a rigorous, long-term data collection project. Their goal was to correlate celestial events with earthly occurrences, from the rise of kings to the flooding of rivers. In doing so, they were unwittingly mapping the clockwork of the solar system, gathering centuries of information on orbital patterns and planetary cycles. This divinatory drive created a framework for empirical study, forcing observers to be systematic and precise in their recordings. The very act of seeking meaning in the cosmos required them to first understand its mechanics. The spatial relationships between celestial bodies, carefully noted for their supposed symbolic importance, became a foundational dataset for astronomy. A priest marking the position of Jupiter in a specific constellation was in effect adding another day to point to a slowly unfolding chart of the planet's 18-year journey around the Sun. This blend of the esoteric and the empirical reveals a profound aspect of the human mind. The quest for spiritual answers often walked hand in hand with the pursuit of practical knowledge. The desire to understand fate led directly to a deeper understanding of the physical universe, proving that our drive to measure the world springs from many sources, some of them hidden in the silent, watchful rituals of the past. Ice itself was a living document for those who knew how to read its pages. In the planet's most extreme environments, ancient observers turned the cryosphere into a sophisticated instrument for measuring the world. Inuit hunters navigating the vast, frozen seascapes of the Arctic relied on the ice's language for survival. They learned to judge the thickness of sea ice by its color and texture, understanding that darker, grayer ice was dangerously thin, while a brilliant white expanse could support the weight of a sled and a team of dogs. The patterns of pressure ridges and cracks were not just obstacles, they were a map. A specific fracture line might point toward a polynya, a life-sustaining opening in the ice where seals would surface to breathe. This was not passive travel, it was active interpretation, where every step was a calculation based on a deep, generational understanding of a dynamic, frozen landscape. Far to the south, in the high Andes, another culture was reading a different icy text. The Quechua people living in the shadow of towering peaks watched the slow, majestic retreat and advance of glaciers. They understood that these frozen rivers were sensitive indicators of the mountain's climate. A period of glacial retreat would open up new high-altitude pastures for their alpacas, while a significant advance could block a crucial mountain pass for years. By monitoring these changes, they were effectively tracking long-term climate patterns and mapping the shifting boundaries of their vertical world. This cryospheric method required a profound adaptation to the environment. It was a form of knowledge written not in books, but in the very structure of the ice, a knowledge passed down through stories and lived experience. To walk across a glacier was to traverse a library of planetary shifts. Each deep crevasse told a story of tensile stress, of the ice river's slow, grinding journey down the mountain. The layers of compacted snow, visible in an ice core, were an archive of annual snowfall, preserving a history of the atmosphere itself. In these harsh, beautiful landscapes, the Earth was not a static object but a breathing, changing entity. The ice was its most sensitive skin, and by learning its language, these ancient peoples became fluent in the rhythms of the planet itself, turning the most formidable environments into profound classrooms for understanding our world's ever-changing nature. The axis of the world was a concept carved in stone long before it was proven in a laboratory. While many cultures used the stars to find north, a select few builders aimed for a far more stable target, the geographic poles themselves. This was not the wandering magnetic north of a compass needle, but the true, fixed pivot point of the Earth's rotation. Achieving this required looking past the immediate sky to grasp the planet's fundamental geometry. The ancient Egyptians demonstrated this with breathtaking accuracy. The Temple of Amun-Re at Karnak, for instance, is aligned not to the solstice sun or a bright star, but directly to the Earth's true North Pole. How could they achieve such a feat without modern instruments? The method was one of profound patience. They likely tracked the path of a circumpolar star over the course of a full night, marking its highest and lowest points in the sky. The midpoint between these two extremes would point unerringly to the celestial pole, the spot in the sky directly above the geographic pole. This was a geometric solution of pure genius, turning the slow arc of a single star into a permanent terrestrial reference. This polar alignment was not merely symbolic. It created a foundation of absolute stability. A road built from a pole-aligned temple would run straight for miles, its course unswayed by the local magnetic anomalies that can mislead a compass. For seafaring cultures like the Norse, who built their iconic stone ships aligned to these true directions, it meant that a bearing taken from a coastal monument would hold true far out in the open ocean. This was a system built for the ages, designed to outlast the precession of the stars or the drift of the magnetic poles. Even a tiny error, a fraction of a degree in the initial alignment, would magnify over a long enough distance, causing a navigator to miss his mark by miles. The fact that these structures remain so precisely oriented is a testament to the rigor of their methods. To stand at the center of such a site is to feel a profound connection to the planet's spin. The entire civilization, in a sense, was anchored to this invisible axis. It was humanity's way of planting a flag on the spinning Earth, declaring that we had found our footing, that we had mapped our place not just on the land but within the cosmos itself. This silent dialogue between the human spirit and the turning world is a legacy written in alignments that still point true after thousands of years. A leaf could tell you where you stood on the planet. The natural world was not a random collection of species but a finely tuned system of living landmarks, each plant and animal a testament to the specific conditions of its home. Ancient travelers moving through unfamiliar territories learned to read this biological script. They understood that a sudden abundance of a particular moss meant they were approaching a high mountain pass, its presence a silent announcement of the thinning air and cooler temperatures. The call of a specific coastal bird, heard far inland, could signal the nearness of a great river that led to the sea. This was a form of navigation that relied on a deep, intuitive understanding of ecology, where every living thing was a data point in a vast organic map. In ancient India, healers and botanists classified medicinal herbs not just by their properties, but by the precise elevation at which they thrived. A plant that only grew on south-facing slopes above a certain height was a living altimeter, its presence confirming the traveler's ascent into a new climatic zone. By cataloging these species, they were unknowingly charting the entire topography of the subcontinent, from the humid lowlands to the frigid high Himalayas. Each plant community defined a geographic boundary, its distribution mapping the unseen contours of the land as clearly as any modern survey. This knowledge transformed the animal kingdom into a dynamic guide. The seasonal migration of herds was not just a spectacle of nature, it was a moving compass. Following the tracks of caribou or wildebeest meant following a path that had been tested and perfected over millennia, a route that inevitably led to water, safe passage, and fertile grazing grounds. The absence of certain creatures was as telling as their presence. A landscape devoid of large predators might indicate a recent human settlement, while a sudden quiet in the forest could signal a change in the weather or the proximity of a natural barrier. This ecological method wove biology and geography into a single discipline. To know a place was to know its life, to understand that the rustle of a particular grass in the wind or the sight of a specific beetle on a tree trunk was part of a larger, measurable pattern. The world was not a silent stage for human journey, but a chorus of interconnected voices, each one offering a clue to the size, shape, and character of the planet we call home. The true scale of their genius was often buried with them. For centuries, the full extent of ancient geographic knowledge remained hidden, its secrets locked within overgrown ruins and indecipherable texts. It has taken our most advanced modern tools to finally uncover what was lost, revealing a precision that continues to stagger researchers. In the dense jungles of Central America, LiDAR technology pierces the canopy, firing millions of laser pulses from aircraft to map the ground below. What it reveals are not just isolated temples, but entire Mayan cities laid out with a geometric master plan. Vast networks of causeways run in perfectly straight lines for miles, connecting ceremonial centers to reservoirs and agricultural fields with an accuracy that rivals modern urban planning. These hidden alignments, invisible from the ground, confirm a level of large-scale geographic coordination we never knew existed. The stones themselves are finally telling their story to a new generation of listeners. This process of rediscovery is a powerful bridge across time. An archaeologist might unearth a ceremonial platform whose orientation seems odd, only to have satellite data confirm it aligns with a distant mountain peak on the summer solstice. A stone tablet inscribed with complex calculations is found to match the path of Venus with uncanny accuracy. Each discovery is a quiet revelation, a moment where ancient insight is validated by contemporary science. It proves that their mastery was not myth, but a tangible, recoverable intelligence. This legacy is more than a historical curiosity. It is a profound inspiration. Modern geodesists, the scientists who measure the Earth, now look to these ancient methods with renewed respect. They see in the knotted cords and star-aligned stones a different way of thinking about measurement, one that integrated the human experience with the physical world. The quest to understand our planet is not a new one, it is the oldest story we have, and as we use our satellites and lasers to peer into the past, we are not just uncovering their knowledge, we are rediscovering a part of ourselves, a relentless drive to map our place in the cosmos that connects the builder laying a foundation stone to the scientist staring at a digital elevation model. They were the first explorers of a world they knew was vast, mysterious, and beautifully measurable. From celestial navigation to geometric ratios, ancient builders employed a stunning array of methods to measure the planet with precision that still amazes us today. Their achievements were not the result of a single breakthrough, but of a patient, collective effort spanning continents and generations. They looked to the stars and saw a fixed grid for navigation. They studied a shadow's length and deduced the Earth's grand curvature. They stretched simple ropes to create perfect angles that would anchor their greatest monuments. Each culture, from the Polynesian voyagers to the Roman engineers, added its own unique piece to this global puzzle, proving that the drive to understand our world is a universal human trait. This legacy challenges the very notion of progress, suggesting that true ingenuity is not defined by the complexity of our tools, but by the depth of our observation and the clarity of our thought. Their work reminds us that human curiosity and ingenuity have always driven progress, even without modern technology. They asked the same fundamental questions we ask today, and they found answers written in the language of the natural world. As we reflect on these timeless techniques, consider how they reshape our view of history and our own potential for discovery. Their story is an invitation to look at the world with fresh eyes, to see the extraordinary precision hidden in ordinary things. If this journey into the past has sparked your wonder, share your thoughts in the comments and subscribe for more explorations into the mysteries that connect us across time. Let's keep unraveling the secrets of our world together, honoring the legacy of those who mapped the Earth long before us.